At 6:42 on the morning of December 8, 1941, the day after Pearl Harbor, a 27-year-old engineer named Jiro Horikoshi walked into the Mitsubishi aircraft plant in Nagoya and understood, with the particular clarity of a man who has just watched everything change, that the aircraft he had spent 4 years designing was now at war. The Zero had been in production for 18 months. Horikoshi had drawn every line of it by hand, had argued for every gram of weight reduction, had personally supervised the metallurgical tests that made it possible. He had created it to be the finest carrier-based fighter in the world. It was. He had not created it to fight a war against the industrial capacity of the United States. He understood the mathematics. Japan produced 436 Zero fighters in 1941. The United States produced 19,433 aircraft of all types in the same year, and the Americans were just starting. What followed over the next 4 years was one of the most audacious and ultimately doomed industrial campaigns in the history of warfare. Japan would produce over 10,000 Zero fighters under conditions that should have made it impossible. Under blockade, under bombardment, under the systematic destruction of the supply chains and factories that the aircraft depended on. They would do it by moving the factories underground, by dispersing production across hundreds of small workshops, by cannibalizing civilian industry until there was nothing left to cannibalize. They would produce 10,000 aircraft, and it would not be enough. Horikoshi's problem in 1937, when the Imperial Japanese Navy handed him the specification that would become the Zero, was weight. The Navy wanted a carrier-based fighter that could fly at 500 kilometers per hour, climb to 3,000 meters in under 3.5 minutes, carry 2 20mm cannons and 2 7.7mm machine guns, have a range of over 3,000 kilometers with drop tanks, and maneuver at low speed better than anything the Chinese Air Force or the anticipated Allied opposition could put against it. They wanted all of this from a single-engine aircraft light enough to operate from carrier decks. The specification was, by the engineering standards of 1937, impossible. Every element of it required trade-offs that contradicted every other element. Long range required fuel. Fuel required tanks. Tanks required structure. Structure required weight. Weight killed speed and climb rate. Armor protected the pilot. Armor weighed. Self-sealing fuel tanks prevented fires. Self-sealing tanks weighed. Every fighter in service with every air force in the world had made these trade-offs and arrived at aircraft that were capable in some respects and deficient in others. Horikoshi refused the trade-offs. He had worked for Mitsubishi since graduating from Tokyo Imperial University in 1927. He had studied aircraft design in Germany and America. He had designed fighters that had been rejected, modified, improved, and rejected again by a Navy specification process that knew exactly what it wanted and was not certain such a thing could exist. He was 32 years old when the Zero specification arrived. He was not arrogant. He was precise, which is a different thing. And he had identified a solution that no one else had reached because it required accepting an engineering risk that conventional aircraft design explicitly avoided. The solution was the material. Sumitomo Metal Industries had developed an aluminum alloy called extra super duralumin, designated 7075, that was significantly stronger per unit weight than the alloys used in standard aircraft construction. It was also more brittle, more susceptible to stress fractures, harder to work, and had never been used in production aircraft. The risk was not theoretical. If the alloy failed under combat stress, it failed catastrophically. The pilot had no warning and no recovery. Horikoshi chose it anyway. He used extra super duralumin in the Zero's airframe wherever the strength-to-weight ratio justified the risk. He eliminated armor plate behind the pilot's seat. He eliminated self-sealing fuel tank liners. He designed the airframe to tolerances that required a level of manufacturing precision that Japanese industry in 1937 had never been asked to achieve. He designed the canopy to give the pilot an unobstructed 360-degree field of view, which required a structural solution that added complexity and reduced weight simultaneously. a contradiction he solved with geometry rather than materials. The prototype flew on April 1st, 1939. It performed exactly as the specification required. Not approximately. Exactly. The Navy test pilots who flew it came back with reports that used words Japanese test pilots did not habitually use about Japanese aircraft. They used words that translated roughly as extraordinary and unprecedented. The Zero climbed faster and turned tighter, flew farther, and carried more armament than anything in its weight class that any of them had encountered. The Navy accepted it immediately. Mitsubishi began production in 1940. The aircraft that American pilots would eventually call the Zero, that the Navy designated the A-6M, that Japanese pilots called the Ryzen, the Zero fighter, entered combat over China in August of 1940. It was, for the first 2 years of its operational life, effectively undefeatable in the conditions where it was deployed. Over China, it flew combat air patrol, escorted bombers, fought Chinese fighters, and produced loss ratios that the Navy's planning staff used to build an entire strategic doctrine around the assumption of air superiority. 13 consecutive kills in its first engagement. 0 losses. By December of 1941, when Horikoshi walked into the Nagoya plant and understood that the war had changed, 521 Zeros had been produced. They were operating from carriers that had just destroyed the American Pacific Fleet at Pearl Harbor, from island bases across the Western Pacific, and from airfields in China that the Army had captured and the Navy had equipped. The Americans did not yet know what they were fighting. The Grumman F-4F Wildcat was not a bad aircraft. This matters because the story of the Zero in the first 18 months of the Pacific War is sometimes told as though the Americans were flying training planes against a combat aircraft, which was not the case. The Wildcat was well built, rugged, and capable in the hands of an experienced pilot. It had armor plate. It had self-sealing tanks. It was difficult to shoot down. It could absorb combat damage that would have destroyed a Zero and bring its pilot home. It was also significantly slower, significantly less maneuverable, and had significantly shorter range than the aircraft it was being sent to fight. The loss ratios in the first months of the Pacific War were not a matter of American pilot quality. The Americans who flew against Zeros over Wake Island, over Darwin, over the Coral Sea were not poorly trained or poorly motivated. Many of them were the best pilots their country had produced. They died anyway, in numbers that the Navy's pre-war planning assumptions had not accounted for, because the aircraft they were flying had been designed without specific knowledge of what the Zero could do. No one outside Japan had specific knowledge of what the Zero could do. The aircraft had been fighting over China since 1940. American military intelligence had received reports. The reports had been evaluated and filed. The evaluation had concluded that a Japanese aircraft matching the reported performance specifications was aerodynamically implausible. The specifications implied a weight-to-power ratio that required either errors in the reporting or capabilities in Japanese aviation that American analysts did not believe existed. The analysts were wrong. Horikoshi's material solution had produced an aircraft that was aerodynamically implausible by the standards that American analysts had applied, because those standards assumed the materials and manufacturing tolerances of American aircraft production. The Zero was built to different tolerances with different materials. The Americans found out on December 7, 1941, and spent the next 18 months trying to build an aircraft that could fight it on equal terms. They succeeded, but that is a later part of this story. The Mitsubishi plant at Nagoya was, by 1942, the most important military manufacturing facility in Japan. It was not the largest. The Nakajima aircraft factories at Musashino and Ota were larger by square footage. The Kawasaki facilities at Akashi produced more engines. But Nagoya was where the Zero was built, and the Zero was what kept the Imperial Navy's carriers operational, and the carriers were what the Japanese strategic planners had decided the war would be won or lost by. The plant employed 13,000 workers by early 1942. It ran 2 shifts, 12 hours each, 6 days a week. The production rate that Mitsubishi's management had committed to after Pearl Harbor was 2 aircraft per day. This required a manufacturing precision that the pre-war production process had achieved only intermittently, and that the expansion of the workforce to meet wartime demand made systematically difficult. The problem was Horikoshi's tolerances. The Zero's airframe, built to extra superduralumin specifications, required machining and assembly accuracy that experienced workers could achieve reliably, and inexperienced workers could not. The pre-war workforce had spent years developing the muscle memory and judgment that the tolerances demanded. The wartime expansion workforce, drawn from factories that built ships, locomotives, and industrial machinery, did not have it. Defect rates climbed in the first months after Pearl Harbor. Aircraft that passed initial inspection failed structural tests. Wings that met dimensional specifications produced aerodynamic behavior that did not match design parameters. The Navy's acceptance inspectors began rejecting completed aircraft at rates that threatened the production targets. Mitsubishi's management brought Horikoshi's engineering team back into the production process. They had been moved to advanced design work on the Zero's successor. They were pulled out and placed on the production floor, working alongside assembly workers, identifying where the tolerances were failing and why, developing production aids and fixtures that reduced the dependence on individual skill that the original process had assumed. The defect rate came down. The production rate climbed. By the end of 1942, Mitsubishi was producing 3 Zeros per day. The Navy's target of 2 had been exceeded. The engineers had made the impossible specification manufacturable at scale by solving the same problem Horikoshi had solved in design. Finding the tolerance that the system could reliably achieve and building the process around it. Then the Americans found the Aviation Zero. On June 4, 1942, the same day that the Battle of Midway was destroying Japan's carrier air power, a Japanese Zero was shot down over Akutan Island in the Aleutians. The pilot was killed instantly, but the aircraft, which came down in a marsh at low speed with its landing gear extended, was largely intact. The Americans found it 3 weeks later. The recovery operation that pulled the Zero out of the Alaskan marsh and shipped it to San Diego was treated with the urgency that the Navy's fighter pilots had been demanding since Pearl Harbor. They needed to know what they were fighting. They had been asking for months. The intelligence system had told them what it could from combat reports and captured documents, which was not enough. Now they had the aircraft. The Navy's test pilots flew it against every fighter in the American inventory. The results confirmed everything the combat reports had described and added specifics that the reports had not been able to provide. The Zero's turn radius at low speed was tighter than anything American pilots had encountered. Its rate of climb in the first several thousand feet of altitude exceeded the Wildcats by a margin that made altitude advantage in combat almost impossible to establish by conventional means. Its range, even without drop tanks, was extraordinary for a single-engine fighter of its weight class. But the test pilots also found the weaknesses. The Zero's controls stiffened dramatically at high speed. Approaching 350 miles per hour, the ailerons became difficult to move, and above 400 miles per hour they were effectively locked. A Zero pilot in a high-speed dive was in an aircraft he could not maneuver. The Zero's engine, superb at low and medium altitudes, lost power above 20,000 feet faster than American engines did. And the Zero, without armor or self-sealing tanks, was catastrophically vulnerable to accurate gunfire. A short burst from a .50 caliber machine gun into the fuel tanks produced fires that the Zero's pilots could not survive. The tactics that followed from these findings changed the Pacific Air War. Do not dogfight the Zero at low speed. Do not turn with it. Attack from altitude, fire, and dive away. Use the Zero's control stiffness against it. Force it to high speed, and it becomes a different aircraft, one that American pilots could handle. The Thatch Weave, the combat technique that Navy Lieutenant Commander Jimmy Thatch had developed from the combat reports, became standard doctrine. High-altitude attacks, team tactics, the use of superior radio communication and fighter control to position American aircraft where the Zero's advantages were neutralized. American aircraft manufacturers began producing the aircraft that would execute these tactics. The Grumman F-6F Hellcat, designed with direct input from the pilots who had fought the Zero and the engineers who had studied the Akutan aircraft, entered production in January of 1943 and combat in September of the same year. It was heavier than the Zero, less maneuverable at low speed, and faster, more powerful, better armored, easier to produce, and in the hands of a trained American pilot following the new doctrine, consistently lethal to the aircraft Horikoshi had built. Japan had to respond. Japan had to produce. The Japanese Navy's planning staff understood the mathematics by mid-1942, even before Midway. At Pearl Harbor, the Navy had attacked with 420 aircraft from 6 carriers. At Midway cost them 228 aircraft and 4 carriers in 4 minutes of dive bomber attacks. The carrier force that had been the instrument of Japanese strategic ambition in the Pacific was reduced in a single engagement to a defensive capability. The aircraft that had been the tool of that force were being consumed in combat at rates that exceeded the production system's ability to replace them. Japan produced 2,935 Zero fighters in 1942. America produced 47,836 aircraft of all types. The ratio was approximately 16-1 and growing. The American production system, which had been converting civilian industrial capacity to military use since 1940, was reaching its wartime production peak. The Japanese production system, which had been running at military capacity since the war in China began in 1937, had less room to grow and less industrial base to grow from. The raw material problem was immediate and structural. Japan imported 88% of its oil, 79% of its iron ore, and 100% of its aluminum bauxite before the war. The strategic calculation that had driven the expansion into Southeast Asia was precisely this: capture the oil fields of the Dutch East Indies, the rubber of Malaya, the bauxite of the Philippines, and the raw material constraint disappears. The gamble had worked in the first 6 months. The raw materials were flowing. The production lines were running. But the shipping that carried the raw materials from the captured territories to the Japanese home islands was being destroyed. American submarines were finding the convoy routes and working them with increasing effectiveness as the war went on. In 1942, American submarines sank 180 Japanese merchant vessels. In 1943, they sank 296. In 1944, they sank 492. The bauxite that Japan needed to smelt aluminum that became Zero airframes was on ships that were at the bottom of the Pacific. The production planners found a partial solution, which was to use less aluminum per aircraft. The Zero's already razor-thin structural margins were pushed further. The manufacturing tolerances that Horikoshi's engineers had spent years achieving were relaxed where they could be relaxed. The result was aircraft that were lighter in the wrong ways, structurally marginal in ways that pilots could not detect until the aircraft failed under combat stress. And then the bombers came. The B-29 Superfortress was not ready in 1943, not in the way the American planners had intended it to be ready. The aircraft was technically extraordinary, a pressurized bomber capable of carrying 20,000 pounds of ordnance to altitudes above 30,000 feet at speeds that made interception by conventional fighters difficult. It had been designed specifically to reach Japan from bases that Japanese air power could not threaten, to fly above the Zero's effective operating ceiling, and to deliver the industrial destruction that the American strategic bombing doctrine assumed would end any modern war. The doctrine was wrong about some things and right about one. It was wrong about precision. The first B-29 raids on Japan, conducted from bases in China beginning in June of 1944, attempted to destroy specific industrial facilities with high-altitude daylight bombing. High altitude meant high winds at the jet stream level that Japanese geography concentrated into velocities that American meteorologists had not fully understood. Bombs that should have hit within 300 feet of a target missed by miles. The Nagoya aircraft plants were raided 6 times in late 1944. The damage was real, but not decisive. The production lines continued. What was right was the principle of targeting. The American planners had identified the aircraft factories as the critical node. Destroy the production capacity, and the aircraft stop. Stop the aircraft, and the carriers become vulnerable. Make the carriers vulnerable, and the island-hopping campaign reaches the home islands. The logic was correct. The execution, in 1944, was not yet capable of following the logic to its conclusion. Mitsubishi responded to the first raids with the plan that every major industrial target under air attack eventually develops: disperse. The dispersal plan that Mitsubishi and the Japanese Military Production Ministry developed in late 1944 was, as an engineering and logistics undertaking, genuinely extraordinary. The Nagoya plant could not be protected. It was too large, too well known, too obviously the target for any bomber force attacking Japanese aircraft production. What could be done was to move the production capacity out of the building and into places that bombers could not easily find or could not easily hit, even if they found them. The primary solution was tunnels. Japan's geology, volcanic and mountainous, provided both the material and the opportunity. The mountains that made Japanese terrain difficult for ground forces to traverse contained rock that could be hollowed out. The Japanese Army and Navy Engineering Corps, which had been blasting fortifications into Pacific Island coral for 3 years, turned their expertise inward. Teams of workers, many of them conscripted Korean laborers, began excavating production facilities into the mountains near Nagoya, near Osaka, near the Nakajima plants in the Kanto Plain. The largest of these underground facilities was at Matsushiro in Nagano Prefecture. The complex eventually extended over 10 kilometers of tunnels, with production floors carved from solid rock, ventilated by shafts that surfaced miles from the main entrance, lit by electrical systems installed along the tunnel walls. It was intended to house not only aircraft production, but the Imperial headquarters and the essential government ministries in the event of an invasion. It was never fully operational before the war ended, but dozens of smaller dispersed facilities were. By early 1945, Mitsubishi's Zero production had been broken into sub-assemblies distributed across approximately 200 separate facilities. The fuselage was built in one location, the wings in another. The engine, which was a Nakajima Sakai radial requiring precision manufacture of its own, in a third. The components were transported to final assembly locations that were themselves dispersed across multiple sites. The transportation that connected these dispersed facilities was the vulnerability the planners could not fully solve. Roads and railways were visible from the air. Now vehicles moving components between locations could be observed and attacked. The system that had replaced one large target with 200 small ones had created a logistics network that was itself a target set. But in the winter of 1944 and into 1945, the aircraft were still being produced. The workforce that built the Zero in 1945 was not the workforce that had built it in 1942. The men who had developed the tolerances, who had learned Horikoshi's specifications through years of practice, who had built the aircraft in the peacetime facilities with proper tools and adequate materials, were gone. They were in the Navy, in the Army, on islands across the Pacific, in the air over Leyte Gulf, at the bottom of the Philippine Sea. The production system that depended on their skill had consumed them. The replacement workforce was students. Japan mobilized its school-age population for war production in 1944. Secondary school students, boys and girls between 12 and 18 years old, were organized into labor brigades and assigned to aircraft factories, munitions plants, and dispersed production facilities. By late 1944, students constituted the majority of the workforce at many production sites. They were not trained. They did not have the years of accumulated judgment that Horikoshi's tolerances required. They had instructions and the willingness of children who had been told that the survival of the nation depended on them. The quality problems that had appeared in 1942, when the workforce was expanded with adult workers from other industries, were worse with teenage students working in underground facilities without adequate tooling or supervision. Defect rates climbed again. Airframes that passed dimensional inspection failed under stress. Aircraft that were accepted by Navy inspectors and delivered to operational units developed mechanical problems that grounded them within days of arrival. The Navy's own records, examined after the war, showed that in the final 6 months of the conflict, the average time between an aircraft's delivery from the factory and its first maintenance-requiring malfunction was 11 flight hours. The pre-war standard had been 200 hours. The aircraft were being produced. They were not the aircraft Horikoshi had designed. Curtis LeMay arrived in the Mariana Islands in January of 1945 as commander of the 21st Bomber Command, with the specific assignment of making the B-29 campaign against Japan produce results that it had not yet produced. He was 38 years old. He had commanded the air campaign against Germany from England. He had developed the combat box formations that reduced bomber losses on European raids. He was not a man who accepted operational failure as a permanent condition. The problem with the B-29 raids on Japan was altitude. The jet stream winds above Japan at 30,000 feet were faster and more variable than American meteorologists had measured over any other theater. Bombing accuracy from that altitude in those conditions was not a military problem that persistence could solve. The physics were wrong. LeMay changed the physics. He ordered the B-29s to fly at night, at low altitude, between 5,000 and 9,000 feet, stripped of their defensive guns and gun crews, to increase bomb load, carrying incendiary bombs instead of high explosives. The incendiaries were designed for Japanese construction. The residential and light industrial districts of Japanese cities were built primarily of wood. Incendiary bombs dropped from low altitude in sufficient density produced fires that spread faster than fire control systems could respond to. The first low-altitude incendiary raid hit Tokyo on the night of March 9, 1945. 16 square miles of the city burned. 80,000 people died in the firestorm. The Sumida River ran red. The bombers that returned to the Marianas had fly ash on their airframes from 5,000 feet altitude. The mission had been flown below the ceiling of effective Japanese anti-aircraft fire. The night had made the bombers invisible to fighters without radar guidance. The stripped aircraft, carrying twice the bomb load of the high-altitude configuration, had covered the target area with incendiary density that no firefighting capability could have addressed. LeMay sent 300 aircraft to Nagoya the following night. The Mitsubishi plant was not a residential district. It had reinforced concrete structures and metal frame buildings that incendiaries could not burn the way wooden neighborhoods burned. But the city around the plant, the housing for the workers, the transportation networks, the electrical substations, the water mains that fed the industrial fire suppression systems, these burned. And then the B-29s came back. The dispersal plan saved the production numbers. This is the answer to the question that the thumbnail of this video poses, and it is worth stating precisely. Japan produced 10,000 Zero fighters despite US bombing, because by the time the bombing became systematically devastating in early 1945, the production was no longer in the buildings being bombed. The Nagoya Mitsubishi plant was damaged in the March raids and again in May. The damage was serious. Production at the main facility fell to negligible levels by June of 1945. But the sub-assembly network, the 200 dispersed facilities, the underground workshops, the school gymnasiums converted to production floors, the rural workshops producing components in villages that no American target planner had catalogued, continued producing parts. The parts were incomplete aircraft. Final assembly required tools and facilities that the dispersed system could not fully replicate in underground tunnels or converted school buildings. The components accumulated at dispersed storage sites, waiting for assembly capacity that was being destroyed faster than it could be rebuilt. By July of 1945, Japan had approximately 9,000 aircraft in storage, of which roughly 4,000 were operational fighters, held back from combat by strategic order. They were being saved for the invasion that American and Japanese planners both believed was coming. The invasion of Kyushu, was scheduled for November. The aircraft would be used as kamikazes, crashing into the landing ships with full fuel loads and 550-pound bombs, and the planners on both sides had done the arithmetic on what 4,000 aircraft, flown as guided missiles against an invasion fleet, would cost in lives. American estimates said 250,000 American casualties, and Japanese estimates were built around the assumption that the cost would be high enough to force a negotiated peace. Neither estimate was tested. On August 6, 1945, a single B-29 dropped a single bomb on Hiroshima. The aircraft was the Enola Gay. The bomb was Little Boy, a uranium gun-type device producing a yield of approximately 15 kilotons. It destroyed 4.7 square miles of the city in the first seconds of its detonation and killed between 70,000 and 80,000 people immediately, with the total death toll rising to 140,000 by the end of the year as radiation casualties accumulated. 3 days later, a second bomb hit Nagasaki. On August 15th, Emperor Hirohito broadcast to the Japanese nation. The speech used the formal court language that most Japanese subjects had never heard him use, had never heard him speak at all. He said that the war situation had developed not necessarily to Japan's advantage, and that the enemy had begun to employ a new and most cruel bomb, the power of which to do damage is indeed incalculable. He did not use the word surrender. The military meaning was surrender. The 4,000 aircraft in dispersed storage were never flown. The teenage workers in the underground factories put down their tools. The engineers who had been designing the Zero's successor, a faster, better-armed aircraft that would have addressed the performance gap that American fighters had opened, folded their drawings and went home. Jiro Horikoshi, who had spent the war trying to get the manufacturing system to build his aircraft to the tolerances he had designed it to, spent the immediate post-war period at his desk writing. He was documenting what he had built and why. The manuscript would eventually be published as Eagles of Mitsubishi, a technical and personal account of the Zero's design that became the primary historical record of how a 32-year-old engineer in Nagoya had produced the aircraft that the greatest navy in history had not been able to detect or predict. He lived until 1982. He saw the aircraft he had designed become the subject of museums and documentaries and eventually a Hayao Miyazaki film. He saw Japan rebuild its industrial capacity, channel the precision manufacturing culture that had built the Zero into automobiles and electronics and cameras that dominated peacetime markets. He saw what precision and the willingness to accept an engineering risk that everyone else considered impossible could produce. He had known that already. 10,430 Zero fighters were produced between 1940 and 1945. The number is significant not because it was enough, but because it was not supposed to be possible. Japan's industrial base, its raw material constraints, its workforce limitations, and the systematic destruction of its production facilities by American bombing should have produced far fewer. The dispersal plan, the underground facilities, the student labor brigades, and the deliberate sacrifice of quality for quantity in the final year kept the number climbing past what the American planners' assessments had predicted. It was not enough. The American production system, running at full wartime capacity, produced 300,000 aircraft between 1941 and 1945. The ratio was not 16-1. By the end of the war, it was closer to 30-1. The quality gap widened simultaneously. The Hellcat that entered combat in 1943 flew faster than the Zero at every altitude above 15,000 feet, was more survivable, easier to maintain, and was flown by pilots who were products of a training pipeline that the American industrial base could sustain and that Japan's could not. Japan destroyed its pilot training program in the first year of the war by using its experienced pilots in combat until they were dead rather than rotating them home to train replacements. The Americans rotated their experienced pilots out of combat and put them in training squadrons. The Zero that was shot down over Guadalcanal in 1942 was often flown by a pilot with 600 hours of flight experience who had been through the most rigorous naval aviation training program in the world. The Zero that was shot down over Okinawa in 1945 was often flown by a pilot with 40 hours of flight experience who had been told he did not need to learn to land. The aircraft were still being produced. The men who could fly them were gone. Horikoshi had built an extraordinary weapon. The system that deployed it consumed the men who could use it faster than any production line could compensate. The 10,000 aircraft sit in the historical record as a monument to what industrial improvisation, engineering precision, and a workforce that included children working by lamplight in mountain tunnels can produce when the alternative is national defeat. It was not enough. It was more than it should have been. And it was built by a man who looked at an impossible specification in 1937 and decided that the specification was correct, and reality would have to be adjusted accordingly. He was right. The war proved it. If this story hit you, like and subscribe. We find these forgotten stories every single day. Drop a comment and tell us where you are watching from, and watch this next video. You are not going to believe this.